Hi everyone, and welcome to another mini course at Physics Latam. Today we are happy to have Anton Fonarev giving an introduction to cohomology in algebraic geometry. Anton is a researcher at Steklov Mathematical Institute of Russian Academy of Science. He completed his PhD in 2014 at the same institute. His research interests are algebraic geometry, derived categories of coherent sheaves, and so many other topics related to these areas. If you have any question during the talk, please do not hesitate to raise your hand. Now I leave you with Anton. Please go ahead.
Thank you very much for the introduction. I think it's a very pleasant opportunity to kind of speak to a broader audience, that's for sure. And I think it's a great initiative anyway to spread knowledge. Something came very nicely out of COVID, which is this online classes. So the broad subject was kind of cohomological methods in algebraic geometry. And of course, modern algebraic geometry is full of them in a way. It all starts a little bit with Grothendieck and before, but let me kind of slowly today give an overview picture of what is happening and how things arise from the very foundation. And the very first thing that comes to mind, of course, is vector bundles, and it happens in a very standard kind of situation. It arises in physics plenty. So in the most general situation, you start with X, just a topological space. And the classical notion of a vector bundle is to each point X in X, you want to associate, well, say, Cn. And as in physics, I don't know, these are probably X is some kind of particle moving or a state, and then you associate various numbers which distinguish things. I'm not a physicist, but I know that these things arise all of the time, and this Cn should vary according to X. So in the simplest case, of course, you have just another topological space E, and you have the projection map to X. And this E, well, in the simplest case, it's just X times Cn. And then how do you recover this Cn? Well, the first thing to recover this Cn is you can look at the following set. You can look at the set of sections. So what is a section? This is the trivial bundle. And to recover Cn, you look at the sections which are maps from E. Here you have your projection map S with the following condition. If you compose S with pi, you get the identity map on X, which is the same as above every point X, you choose an element in the fiber. So a little point X, you associate an element which is just a vector in the fiber in Cn. So this is all very nice, but very quickly, you often see that it's, well, non-trivial, the Cn varies with respect to X. And this is the classical notion of a vector bundle, again, in the topological sense. So what is a vector bundle? You're looking at a map from E to X, a smooth map. Now, above every, well, the first, that the fiber phi inverse of X small is always isomorphic to Cn, so this is your vector space. But this is not enough. You actually want to vary nicely in the sense that you want to keep this vector space structure. So keep the vector space structure. All right. So how do you keep the vector space structure? Well, in order to keep the vector space structure, this is what you do. You want to say that it's locally trivial so you can choose, this is important, that you can find an open covering. So what's a covering? A covering is a representation of X as a union U alpha, where these are open. And now above, there are two conditions. First, above each U alpha, you have that E restricted to U alpha, which is nothing but the full inverse image of U alpha. Here you have your projection to U alpha. And now this must be isomorphic to just the direct sum times Cn. Here you have the natural projection map, P1, the projection on the first coordinate. Here you have the identity map, identity. And this thing should commute. This is just a formal representation of what it means to be locally trivial. But locally trivial is not enough, because sometimes, of course, you have intersections. So the second condition is above each intersection for two charts, U alpha intersected with U beta. Well, now you have the following nice picture. You have U alpha beta. Let me denote this by U alpha beta. Well, it's an open subset, so it embeds on the one hand into U alpha. On the other hand, it embeds into U beta. Now above here, you have the restriction of your bundle to U alpha beta. Of course, this guy maps to the restriction of your bundle to U beta. Here are the projections, and here's the restriction to U alpha. So what we have now here is we have a certain isomorphism of U beta times Cn, and here you have another isomorphism of U alpha times Cn this time. I'm sorry for those who know the stuff already, but since we're going to vastly generalize it soon then, or see how it works in algebraic geometry, I mean, this is necessary to remember. This is the first projection, and this is the second projection. So what we do now above U alpha beta, if you look at the corresponding arrows, what you will have an isomorphism of U alpha beta times Cn, which comes from the left-hand side, which comes from U alpha being an open subset inside U alpha beta inside U alpha. And this becomes isomorphic in one way or another to U alpha beta times Cn. And this isomorphism is compatible with the two projections. So what does it actually mean? It means that above every point inside U alpha beta, we have two different ways of identifying the fiber with our vector space. So we get a certain map that I will denote by phi alpha beta. And phi alpha beta is compatible with the projections to U alpha beta. So what does it mean? It means that to each point x in U alpha beta, we associate an isomorphism of the fibers Cn with Cn. So in general, this can be arbitrary. So this is exactly phi alpha beta of x. This could be arbitrary, but what we want to do is we want this phi alpha beta to be linear and very nicely with respect to x. And this is where you can ask yourself what kind of geometry you want to do. So what you get is you get a map from U alpha beta. This is the map phi, if you wish, phi alpha beta, to, well, if you want it to be linear and very nicely, then you get a map to the general linear group of Cn, isomorphism of Cn with itself and linear. And now this phi alpha beta can be smooth, can be just continuous, or it can be algebraic. I mean, there are all kinds of notions that you might ask yourself. So we will be interested in algebraic vector bundles. But nevertheless, with vector bundles, so vector bundle, the first thing you associate is you associate global sections. And this is the most important thing that you want to compute kind of in all the applications. So again, I suspect that these sections correspond to some physical fields or other things. But basically, again, a global section is nothing but just a section which is a map from here to here, S, with the property that phi composed with S equals the identity map of X. And the first thing that you realize is that, for instance, first, global sections form a vector space. And second, actually, one can multiply a section by a global function on X, by a global function on X. So the problem in all cohomology in algebraic geometry basically comes from the problem of computing global sections of various algebraic bundles and not only. So if these two things are satisfied, for instance, what you immediately get is that global sections, which I will denote by gamma of X of the bundle E, is a module. So it's a module over the ring of global functions. And in a way, one can start a lot of things and start discussing algebraic geometry from the following theorem. So this is a theorem which is usually attributed to Serre and Swan, or sometimes solely Swan. So let X be a smooth manifold, differentiable manifold, not necessarily compact, then, and let C of X be the algebra of C infinity functions on X. Then there is, well, if you wish, a bijection between isomorphism classes of differentiable vector bundles on X and finitely generated projective modules over this ring C of X, which is a massive algebra. It's a massive, very difficult algebra. And this is given by associating to every vector bundle its module of global sections over X. So this is where you immediately see that instead of studying vector bundles, you can study finitely generated projective modules. And I quickly recall that there are two definitions of finitely generated projective. If A is, say, a commutative ring for simplicity, then P is finitely generated projective. Well, in pedestrian terms, it's a corollary of the general definition. There are several definitions. So if and only if, let me write it this way. First, P is a direct summand in some free module a to the n. Second, the functor hom from P to anything, which goes from A modules to A modules. Let me see which direction. Yes, is exact. So it preserves short exact sequences. Well, and the third one, which we don't need right now, there's a certain universal property of lifting. So here is the big problem then. So let's switch to algebraic geometry. So in algebraic geometry, we have the same situation, the same definitions work. Just replace what? Well, replace all the maps with algebraic maps. And for instance, there's one thing that doesn't work anymore. The series one theorem doesn't work. And the biggest problem is when you start with X, which is compact in geometric sense, which is, well, basically, let's say complete or projective. Even if you take the projective line, P1, I hope everyone remembers what it is, then there are very few functions. Then gamma of P1 of the structure sheaf of X, well, which is the same as just global functions. Then unfortunately, this gamma P1 of O of X is too small. In the differentiable category, you can find plenty and plenty of global functions, but here is just simply the field. Let's do everything over C. I mean, simply the field C. So of course, over C, as you know, there are, what is a finitely generated projective module, just a vector space you cannot go from. So what is the solution? The solution is, well, first of all, let's switch to something else. Let's switch to locally free sheaves. So as you probably remember from your algebraic geometry 1, what is an algebraic variety, or more generally a scheme? It's a variety is what we call a locally ringed space. And a locally ringed space is by definition a pair which comes with this sheaf of rings on it. So this is a sheaf of rings. Which means that to any open subset U in X, we associate the ring of nice functions, of algebraic functions. So what do we have now? You observe that the definition of an algebraic vector bundle, if E over X is a vector bundle, then to each open subset U in X, you associate local sections. Which means that I'm looking simply at the pre-image. If this projection map is pi, I'm looking at the pre-image of U. There is a morphism to U. And I'm looking at local sections S, which once again satisfy the same property, pi of x equals the identity. So as you will see, now locally, every x looks like an affine variety or scheme, which is given by the spectrum of some ring A. And if your bundle pi inverse of U is trivial, then what you have is you have the following picture. Here is U, which is spec of A. Here is the inverse image of U with the projection. And we know that it's isomorphic to U times A to the N. But what is U times A to the N? So we want to compute spec of A times spec. Well, if you're over a field, then K of x1, xn. And you learn in algebraic geometry 1 again that multiplying what it does on the ring of function, this is the same thing as spec of A of x1, xn. So you have this spectrum. Now this is isomorphic to the spectrum of A, x1, xn. You have a morphism here, which corresponds to the projection of the first argument. That's denoted by P1. And remember that there's an equivalence of categories between affine varieties, which are spectral rings. If you have a map from spec B to spec A, then you have the corresponding map from A to B, which is given just by the map on the global function. So this corresponds to a map from A to B. What is the map which corresponds to this P1? The projection from spec of A of x1, etc., xn, from this guy to this guy, is just, of course, the inclusion of constants. If this is the projection of the first argument, then this corresponds to A included in A of x1, xn. But now I want something further. I want to find a section here, S. So a section, spec of A, x1, xn here, and now I have a map in the opposite direction, the spec of A. And this corresponds to some just map from the polynomial algebra, x1, xn, mapping to A. And now what this does is it simply, an arbitrary map would map xi to, well, something, to an element, to an element AI. And the compatibility specifically says that it maps constants to constants. To constants. So this comes from this rule of composition. S composed with pi is the identity map on U. So in particular, you see that sections over U are in one-to-one correspondence with collections of elements A1, AN in A, and this is, of course, nothing but the trivial module A direct sum M. So what we've recovered that Serre-Swan for trivial bundles over, well, there's one for trivial bundles over spec of A, kind of holds. So every trivial bundle, you associate a free module. So of course, sections. Now the next step is what we've recovered is sections form a sheaf of modules over the sheaf of functions of X, which means that for every U open in X, we associate a module, let's call it E of U, over regular functions over U. I mean, this holds not just in the algebraic situation, it holds in arbitrary situation, of course. And if over U E is trivial, then E of U is isomorphic to OX of U, direct sum N. All right. So more generally, one has an equivalence. Well, let's say a bijection for simplicity now, before we have a nice category. One has a bijection between vector bundles over X and locally free. So this is an important part. Sheaves of OX modules. So let me briefly decipher. Again, historically, this is more or less how it goes. So what are sheaves of modules? OX is a sheaf. So this is a sheaf of modules. Meaning that to each U, we associate E of U, which is an OX of U module. And this is compatible with restriction, meaning that if V is in U, then you have a restriction map from E of U to E of V. This is the restriction map, which is a part of the definition of a sheaf, if you want, a tree-sheaf. And this should be compatible with the module structure. So let me, instead of writing the diagram, let me just say this. If S is a section over U, and F is a global function, well, sorry, a function defined over U, then you can multiply a section by a function. So this is, again, a section over U. And now this compatibility says something absolutely trivial. So now you can restrict S to V. You can restrict F also to V, a function restricted to an open subset. And you can multiply the restricted section by a function. And this must be the same as first acting by the function and then restricting. So that nothing happens. It's a very trivial observation. And finally, locally free. It means something very, very simple. Locally free means that specifically for every point, X in X has a neighborhood containing X such that E of U is a trivial module and the same for every V sub u, meaning that you are restricting from E of u, which is isomorphic to O of u to the direct sum n. This can be restricted to E of v, which is isomorphic to O of v direct sum n. And this is just the restriction map for O of x times n. So each function just simply restricts to a function. So I'm slowly approaching the definition that everyone or most of you probably know, but this is again for the sake of maybe historical development or those who have not seen it or don't remember it very well. So there is a nice property of such sheaves of modules. And let me explain this property in the following way. So the property is when we restrict sections to sufficiently small neighborhoods, we do not get any, well, so-called new sections. So why did I put new in this quote? Well, let's look at the following situation. Let's say that U is affine spec of A, and let's look at an open subset V, which is the set where a single function doesn't vanish. This is usually called the principal open subset. And then you learn that this is nothing but spec of A localized in F. And this inclusion corresponds to the natural map, of course. A goes to the localization of A over F. So now if you have a sheaf of modules, what I want to is for the sections of these modules, say E of U, here is a module over A, which is what? Which is the sections OX of U. And in our case, this module is nothing but A to the power n. So what happens with E of V? Well, this is a module over A localized in F, which is global functions OX of V. And now the corresponding map is the map from A to the n to AF to the n. So let me rewrite it in the following manner. This is just a module M, which is an A module. This is a module M restricted to V, which is an AF module. Now, what we need to have is we need to have a map from the M module M to the AF module, which is compatible with the structure. Both, of course, you can multiply by functions on U, but you necessarily, if you have an element here, then you should be able to multiply it when restricted by an arbitrary element in A localized in F. Well, what we have is we have a map restriction of sections. Any section over U can be restricted to a section over V. So how can we make the a module from an A module, we want to make an AF module, which means that we want to be able to multiply by an arbitrary section over V. Well, the easiest possible way to produce such a module is via, of course, tensor product. So the condition here is that this module is actually isomorphic to the tensor product AM over A over AF. So the sheaves of modules that satisfy this condition are called quasi-coherent. So the condition is, let me put it once again, the definition of a quasi-coherent sheaf. Let me first define a quasi-coherent sheaf for an affine open subset. I mean, you can of course, immediately generalize it. So if X is a spec of A, then a quasi-coherent sheaf is a sheaf of modules of OX modules such that, well, let me put it this way. If D of F sits inside X, then the corresponding restriction, let me put this E of X, which is a module M, restriction map to E of D of F. This will be just the localization map, E tensor AF over A. This is not the very best definition, but this is just a way to define it. And secondly, if X is arbitrary, we want an affine covering, meaning a covering by affine open subsets. X is the union of U alpha, such that if you restrict your sheaf of modules to U alpha, I restrict the whole sheaf. So I'm looking at sections over open subsets that are inside U is quasi-coherent. And I will give examples just in a second, but the thing to remember is that first, so properties. The main properties for us are the following. First, well, of course, this definition is independent of the covering. And by this, I mean, by the way, it's a certain technical theorem, but even if you start with an affine spec of A, then you can say, okay, what if I manage to cover a spec of A using definition number 2? And this independent of the definition specifically says that if you have a quasi-coherent sheaf according to 2, then in particular, it's quasi-coherent in the first sense. So there is something to check, which is a certain check. So this definition is independent on the covering. What is more important is that if X is spec of A, then this global section functor, which associates to a quasi-coherent sheaf its global sections, which we denote by gamma X of E, and this is nothing but E of X, gives a bijection between, well, up to isomorphism A modules and quasi-coherent sheaves. So of course, a bijection is not a very nice, I mean, combinatorics, it's fine, but most of the times you want some extra structure. So the extra structure, of course, there's an equivalence of categories. Here you have quasi-coherent sheaves on X, and this is equivalent, in this case, to A mod. So these are all A modules. So in particular, here, what are morphisms? Morphisms are morphisms of sheaves of modules. Sheaves of modules. And what do we have here? We have here, of course, we have morphisms are homomorphisms of modules. And what do I mean by morphism of sheaf of modules? It means that if I want a morphism from E to F, then for any inclusion map, well, of course, for every open subset, I have the corresponding morphism here. And if this is restriction, so this should commute and respect the module structures. And let me stress once again that the module structure is just the structure of multiply by a function. All right, the next property. So this is, again, a certain statement that you can read in a textbook, but now quasi-coherent sheaves for, this is important, this is X is affine. Again, X affine. The next property that we want, which is important, which is 3, actually turns out that quasi-coherent sheaves form an abelian category. So what does it mean? It means that it behaves exactly like the category of abelian groups or the category of modules over a ring. So you can add morphisms, take kernels, take co-kernels, and these are all defined in the same way as for sheaves of abelian groups. This is very important in what comes next. So you just forget all the structure of modules. Well, once you define the kernels, you have your morphism should respect something, but then the structure, but then the only thing you do is you just take the kernel or the co-kernel as just the map of sheaves of abelian groups. And its structure of the module over a sheaf of rings will be preserved. So then fourth is, we extracted this definition from the very thing, is that quasi-coherent sheaves contain all locally free sheaves which is the same as vector bundles. But then there is something nicer that happens to this. So they contain all locally free sheaves. And the final thing is, which is very important, is that there is a smaller category. So assume the technical part that X is Noetherian, which always holds for classical varieties. Then there is a nice smaller, is a nicer category, the category of coherent sheaves. And coherent, if you look at the definition of quasi-coherent, is in the affine case, we assumed that there is this module which generates all the sections. So the thing that we ask for coherence is for this module to be finitely generated. Well, we don't want arbitrary sections, and this always holds, for instance, arbitrarily large sections, and this holds for locally free sheaves. Locally free means that locally the sections are just finitely generated free modules. You can define coherent sheaves in more general settings. It's just that the definition will be a little bit different. But coherent sheaves, meaning that locally on affines, these are given by what? These are given by locally, by finitely generated modules. So in the non-Noetherian case, you replace the definition of you replace finitely generated by something what is called a coherent module, but this is probably outside our discussion. So the most important thing is now 6. You can think of coherent sheaves as some abelian envelope of the category of vector bundles. Meaning that in a certain sense, I won't make it precise, it's the smallest abelian category that contains the category of vector bundles. And namely, let me decipher this a little bit. So what is a morphism of vector bundles? Well, in our terminology, it's the same as the morphism of locally free sheaves. Free sheaves. But comparing to the classical definition, it might not have constant rank. Might not have constant rank. And here is the most typical situation. You start with P1, then you pick a point P inside P1. Then to this point, you can associate the ideal sheaf, I, the ideal sheaf of X, which is over U. These are all functions on U vanishing at your point P. Then it turns out that I is a line bundle. So this I is isomorphic to what we call O of -1. This O of -1 is actually, if you want, corresponds to the tautological bundle, which means that to every point X the fiber over every point x over P1, we associate the line L inside the two-dimensional space inside C2, which corresponds to X, right? What is the projective space? The projective space is the variety parameterizing all lines in a fixed vector space. So here, above every point, which is a line, we can put the line itself. Then what we have is we have a short exact sequence O of -1. These are functions. We think about this as the ideal sheaf. This is a locally free sheaf, and this ideal sheaf is maps. Functions vanishing somewhere are functions. So this gives us a morphism into O of X. And it turns out that here we have some very strange but very nice sheaf of P. And this OP of U is what? It's isomorphic to just your base field C if X belongs to U, and it's 0 if X does not belong to U. And this is a classical example of a coherent sheaf, but not a vector bundle. And similarly, the ideal sheaf of any closed subvariety or subscheme of any closed subscheme is quasi-coherent. So in particular, if Noetherian, then coherent. Sometimes, as we've seen, it's even locally free. All right, well, why all this machinery? Well, this machinery, we genuinely want to think about morphisms of vector bundles. So yes, by the way, another way to think of coherent sheaves, another way to think of coherent sheaves is vector bundles plus structure sheaves which means that the quotients OX by I of closed subschemes. However, so far, very little cohomological stuff, but what we really want to do is we really want to go back to the very first problem that I stated, is that what we actually want to do, we want to compute global sections. And we want to compute global sections most of the times by splitting. Sometimes you can compute it by hand, but we want to split our vector bundles into smaller pieces. And by this, in the most general situation, well, one of the ways you can split is to write your vector bundle as an extension, meaning that you have a subbundle in here, and you have some, if it's of constant rank, then you have E double prime, which can already be a vector bundle as well. So we want by splitting vector bundles into smaller pieces. Here is a big problem. If you have a short exact sequence like this, then we have this functor gamma of X, which sends each quasi-coherent sheaf or locally free sheaf, or technically any sheaf of modules over our ring. So the only thing we can ask is to multiply the section. This functor, which goes to from E to what? Well, it goes to OX modules, OX of X modules, it is not exact. Meaning that the only thing you can say is you have a left exact sequence, E prime of X goes to E of X goes to E double prime of X. Actually, remark that this functor, it not only goes to modules, you can forget that it goes to modules. Actually, its modules, you can forget the module structure and you can go straight to abelian groups, which is the same as Z mod. Oh, big one. And then this functor, which it's still not exact because the only thing we did is we forgot the module structure. Well, you forgot the module structure, no problem. Exactness does not depend on the module structure. I mean, being an exact sequence of modules, it requires, but the underlying kernels, co-kernels is defined solely in terms of the addition structure, meaning abelian groups. And probably everyone's favorite example is not from the algebraic standpoint, but from our example, let's look at P1. Let's do a computation. And then what you have is you have the so-called Euler sequence in which you start from O of minus 1, something we've talked about, and then it goes to the trivial bundle. Let me write it as V times O of X, which is the same as if this P1 is the projectivization of P of V, where V is a two-dimensional vector space. And this is just, you can think it as the direct sum of two copies here. And the quotient is isomorphic to the so-called O of 1. So brief recollection of how line bundles on the projective space work. Line bundles on the projective space, well, say on P1 for simplicity, there are infinitely many isomorphism classes. So to each integer Z, you associate a line bundle of N. And what is this line bundle? So it's trivial over each chart, standard chart. So let's say the homogeneous coordinates are x0 and x1, and u0 is the set where x0 is non-zero, and this is isomorphic to, well, spec of k of x1 over x0. Then u1 is the set of points x1 not equal to 0, which is isomorphic to spec of k of x0 over x1. And then the intersection, u0 intersected with x1, is isomorphic to spec of k of x0 over x1, x1 over x0, meaning that these are two variables that if you multiply them, you get 1. But let me, for simplicity, rewrite it in the following sense. So here you have the intersection. I will introduce just one coordinate. The corresponding maps are, this is k of t inverse. These are functions. I just renamed the variable as t inverse. So this is over u1. Here you have k of t inverse Laurent polynomials over u01. And here over u0, you have k of t u1. And of course, inclusions from u01 to this is u0. u01 to u0 and u1, they correspond to natural maps from k of t in here and k of minus t in here. So now I want to glue a line bundle for each integer n. So my line bundle of n. It will be trivial, the trivial module, but it's the trivial rank 1 module. It's of n, so it's of rank 1. So I will simply have a certain polynomial here. The module m is the trivial module k of t. It's trivial. When I restrict it to u01, then what I get is I get a certain element. So this is isomorphic to k of t inverse. Then I have an element here. Okay, I have, sections over u1, which is k of t1, restricted to u01, which is isomorphic to k of t inverse. And now I need an isomorphism of modules over, I need an isomorphism of this trivial module and this trivial module over the intersection. I need to pick an isomorphism. So the isomorphism over u01, it will do the following thing. It will take my section, take a section over u0, restricted to u01, and then multiply by t to the power minus n. After you multiply by, of course, multiplication by t to the power minus n is an isomorphism of the trivial module with itself, because t to any power is invertible in this ring of Laurent polynomials. Again, in this ring here, t to any power is invertible. So in particular, multiplying by t, the module will give an isomorphism of any module with itself, in particular with the trivial module. So this helps you immediately. It helps you compute. One can now compute the global sections of this bundle of n on P1. And to compute them, of course, what is a global section? A global section is, if you wish, a section we need a section S0 over of n of u0 and S1 over of n of u1, such that S0 restricted to u01 is the same as S1 restricted to u01. So let's unwind it. What we need is we need a polynomial p of t, which is an element of this trivial modules here. And we need a polynomial q of t inverse, which is an element in here. It's the trivial module over t inverse, such that when restricted, p goes to q, which means that t inverse, t to the power n inverse, times p of t equals q of t inverse in k of t inverse. What do you see immediately? You see immediately that if n is strictly less than 0, then there are no such pairs. Why? Well, you start with the polynomial here, which is, of course, it depends on the variable t, And if n is less than 0, then you're multiplying it by t, so you still get a polynomial in t, and moreover, a polynomial of with no constant term, while q is a Laurent polynomial which has no monomials with positive powers of t. So they cannot be the same. This will depend only on t inverse. There are no powers of t, of positive powers of t in the representation of q. And in particular, what you immediately get is you get that there are no global sections on x of O of -1 and O of -2, and of course all the other guys. However, if n is greater or equal than 0, then any p of t of degree less than or equal than n gives a section. And actually, these polynomials, if you homogenize such a polynomial, moreover, if you make it of degree n after you make it a homogeneous polynomial, you see that the global sections over x of O of n is isomorphic to, well, symmetric it's isomorphic to, sorry, let me write it this way, to homogeneous degree n forms on V, which is isomorphic. It's our vector space. So it's a homogeneous polynomial in two variables of degree n, and this is the same as Sn of V star. So this holds for every En, actually. This is a part of a very standard computation. And now let's return to our short exact sequence that we started with. This was my short exact sequence. So let me take this sequence. 0 goes to O of -1, goes to, well, let me write it as 2 copies of the trivial sheaf goes to O of 1. I explained what all the terms are. A good exercise is to check by hand that the quotient of this map, the inclusion map, is indeed isomorphic to the line bundle of O of 1. And now one can, there is this operation of tensor product of vector bundles and more generally of quasi-coherent sheaves which takes two modules, E and F, to quasi-coherent sheaves and produces a new sheaf, tensor product over O of X. And the condition is the following. You take U, and the sections of the new sheaf will be the tensor product over the corresponding ring of the sections. And this gives you a pre-sheaf. And the next thing you do is you sheafify. So now the important thing is tensoring with a locally free sheaf is an exact functor. So in particular, I can start with this. Let me denote this by star. If you tensor this star with O of minus 1, then what you produce a short exact sequence of the form O of minus 2 goes to O of minus 1 plus O of minus 1 goes to O goes to 0. And here I use the following simple property. I want everyone to verify once and for all that O of n tensored with O of m is isomorphic to O of n plus m. All right, we have this new sequence. Now let's apply global sections. Take global sections. What we have is now the global sections of this thing. We have computed global sections of line bundles on the projective line. This is -2. So the parameter is negative. We get 0. Goes to 0 because we have 2 copies of O of minus 1. And the next thing is the global sections of the sheaf of functions. But the sheaf of functions, you know that the functions on the projective line, which we have just rediscovered, are just constants. So we have C. Now, this sequence is not exact. This is not exact. Not exact. It's only left exact. And believe me or not, the whole idea of cohomology, of course, you can apply all possible explanations and you can find many, many applications, and it's beautiful. And I believe that in its own, it's more interesting than global sections. But the very general idea comes from this very simple fact that one wants to compute global sections of certain things, and one cannot efficiently use short exact sequences because taking global sections does not preserve exactness on short exact sequences. One would really want that the global sections of this bundle, if it were global sections of the left term and the right term, but 0 is by no means 0 plus C. We got too much on the right. We got too many quotients. So cohomology solves this problem. Cohomology solves this problem and solves it very, very efficiently. So what things do you need to know about cohomology? Remember, is not even the construction, but the following very, very general property, which actually makes it unique up to isomorphism when defined. So to solve this problem, what we want is to solve non-exactness of this global section function. So what one does, let us solve this not for modules, let us solve it for sheaves of abelian groups on a topological space. So forget about algebraic geometry. After all, for any scheme, you have the underlying topological space. Forget about the sheaf of modules. After all, the sheaf of modules is a sheaf of abelian groups. Yes, you have actions, you can multiply sections by a function, but let's forget about it. We can just add sections together and we can restrict them. And this is always a morphism of abelian groups. So we want for any short exact sequence of groups, what one does is one constructs new functors So the functors will be hi of x, which these functors will go from the category of sheaves of abelian groups on X. So this is the category of the sheaves of abelian groups on X. To every such sheaf of abelian groups, we will associate just a new abelian group. This is one part of the data. And an extra thing for any short exact sequence of such sheaves, E prime goes to E double prime goes to 0, we construct a certain morphism from Hn for any n on X of E double prime to Hn plus 1 of X of E prime. Let me call it delta n. So this is a connecting, the so-called connecting homomorphism. And here I did not write down that delta n. Well, maybe we should write this. This delta depends on the whole extension. For every short exact sequence, we get a certain map and any n greater or equal than 0 with the following properties. With the following properties. And our properties will be very simple. First, H naught of X is just the global sections functor. So just global sections. And second, which is probably the most important part, is for any short exact sequence, E, well, let me write it this way, F, G, you get an associated long exact sequence and here you remember that the global sections functor is actually left exact. This is the most important thing. So it always starts with just global sections over X of E, global sections over X of F, global sections over X of G. And now this, you know that this is a left exact functor, so you cannot continue. But let's look at the next one, which is x1 of X of E. Since it's a functor, we have natural transformations associated to any map. So in particular, since E maps to F, we have a morphism from H1 of E, which goes to H1 of F. Since F maps to G, we have a morphism which goes from H1 of F to H1 of G. So then we have H2 of X, E, etc. And now recall that gamma is oh no, it doesn't work like this, sorry. Recall that gamma is just H naught. And we have a short exact sequence. So here we can put delta 1, which is specifically this delta. We have a short exact sequence, and we have a connecting homomorphism delta n, well, delta naught in one case, which goes from the rightmost bundle or sheaf to the leftmost. So we want this sequence where this will be delta 1 to be exact, meaning that it's exact in all terms, and moreover, this is what we say functorial in short exact sequences. And well, let me write it briefly. If you have E, F, G, and you have another short exact sequence, E prime, F prime, G prime. And if you have morphisms and everything commutes, then you get a map, a morphism of long exact sequences. Or if you wish, you can rewrite it in a simpler way. You can say that so this is an alternative way, that you always get a commutative square of long exact sequences for any n, where this is the first connecting homomorphism, hn plus 1 of x. E delta n, here you have hn of x, g prime, which goes to hn plus 1 of x, e prime, you have the connecting homomorphism delta n prime. And then since I said that my hi are functors, the following two arrows, the vertical ones, they come simply from the fact that a morphism of short exact sequences gives you vertical morphisms here. So this should always be a commutative square. This is another thing to do. But the most important thing that people remember about are these long exact sequences associated to short exact sequences. All right. So in particular, there are various ways to solve this problem that we've stated. So the question is now, finally we get to two, how to construct cohomology, how to construct these functors. These functors. So let me answer this question briefly today. So there are two classical ways to construct these functors. And the first one is the general construction of classical derived functors. And the second one is the Czech cohomology construction. So both of them, interestingly enough, have advantages. So this one is easy to compute, but kind of hard to verify. Well, to check correctness. This one is impossible to compute. And I will explain in a second why. And easy to verify correctness. Check correctness of the definition. So let me probably start with the first one, and then I will talk about the second one briefly. I will do the classical one in a very particular case. So let's do the classical one. Well, let's say for quasi-coherent sheaves or for coherent sheaves. Well, or quasi-coherent. You'll see why I need quasi-coherent in a second. And the solution is the following. Remark that there is actually an isomorphism of functors. Namely, taking the global section over X of a quasi-coherent sheaf is the same as, believe it or not, taking a homomorphism from the sheaf of regular functions on X into X, where this happens in the category of quasi-coherent sheaves. So what is written here? It's written, well, the map in one direction is very easy to define, namely OX of X maps to, so you have a map from, sorry, you have a map, a morphism of sheaves, which is phi, to something, to say E, and this homomorphism maps to phi X, so in particular, OX of X maps to E of X by phi of X. So phi of X is now a morphism of OX of 1 modules. This is a free module, and in particular, free rank 1 module is defined by where it goes. So phi sub X of 1, phi of X of 1, just the constant global 1 function, is specifically the section of your, corresponds to the section of your bundle, it's the section. And vice versa, if you have a section or if you have a global section, you can define this. Well, quasi-coherent, you can actually remove this quasi-coherent and you can just put OX modules, which is not necessary for us at this point, but it's very important. So I replaced one functor with another. And now you can use the machinery of classical derived functors. So what is this machinery? You start with A, which is an abelian category. And say you have a functor f from A to abelian groups such that f is left exact. And a typical example is specifically f equals hom from any object x into anything. This is an example of a left exact functor, meaning that if you have a short exact sequence, remember in the abelian category, you can say kernels, co-kernels. So a short exact sequence is just a sequence where X is the kernel of the map from Y to Z, Z is the co-kernel, all the usual stuff works. Then to this, you'll get just a left exact sequence of abelian groups. Yeah, by the way, maybe I didn't say it specifically. I somehow assumed that left exactness is known. So left exactness is when just the last map is not surjective, but the rest of the properties hold, meaning that f of x is just the kernel of the map from f of y to f of z. So this is an example, as an example. Assume A is what is called has enough injectives. So I need to decipher what has enough injectives means. And we begin with the definition. By definition, an object I in A is injective if it satisfies the following universal property. Well, there are two ways to define this. but an object I is injective, one can say that if the functor hom into I is exact. So you can write the corresponding universal property, but let me just say that this functor is exact. Has enough injectives. A has enough injectives. If hom, if any object X in A can be embedded into an injective, meaning that there is an injective map, a monomorphism from X into I. Then, a big theorem, there exist functors, let me denote them by Rnf from A to a billion groups for n greater or equal than 0. And well, natural transformations as before for any x, y, z. So you might guess where I'm going. Rnf of z to Rn plus 1 f of x delta n. So for any n greater or equal than 0, such that first R naught f is the same as f. Second, for any short exact sequence x, y, z, you get a functorial long exact sequence, which goes 0, goes to f of x, goes to f of y. So it's not writing here. Goes to f of z, goes to R1f of x, goes to R1f of y, goes to R1f of z, goes to R2 f of x, etc., where this is delta 1 and this is delta 0, and it's infinite and it's functorial in short exact sequences. And these functors, by the way, are unique up to isomorphism if you request this property of the long exact sequence and the first one. So these are unique up to isomorphism if 1 and 2 hold. Okay. So what is the construction? The construction is rather bizarre, but just as a note, the construction is you start with your object X, you embed it into injective 1 I naught, then you take the quotient and you denote this by x1. Then you take x1, embed it into I1, you take the quotient x2, etc. So what you get is you get a long exact sequence of the form x0, I0, I1, because the quotient embeds into I1. Then now the co-kernel of this map is x2, x2 embeds into I2, etc. Now you take off x, you look at x at I1, I0, I1, I2, etc. Then you apply f, which is f of I0, f of I1, f of I to etc. And now this is a complex, meaning that each map is the composition of any two consecutive maps is 0. So you put RIF of X to be the ith cohomology of this complex of f of I, meaning that you take the quotient of the kernel of the map from f of I to f of I plus 1, and you quotient it by the image of the map from f of I minus 1 into f of I. And that one is contained in the other. This is specifically the fact that the sequence above is exact. So we also need to show that it's a functor in some way, construct morphism on maps and independent of the choice of the choices. So we chose a lot of injective guys everywhere and many more things. So this is the downside of this definition. By the way, I'm not updating, am I? Is it working? Wait. Share. Screen. Broadcast. Okay. We're back. So, and many more things. Good news. Has been done. And this is basic homological algebra. So now what we do is to construct cohomology. We need to show we need a left exact functor which is specifically our functor of the form. Well, we didn't even need that it's of the form Hom, but it is of the form Hom. Actually, I wanted to say that it's Hom for another reason, but it's gamma of X. And enough injectives. So this enough injectives is a very bizarre thing, because if you ever studied injective modules anywhere, then you must know that injective modules, say over rings, are massive, 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 massive things. So enough injectives for sheaves of abelian groups can be done. And maybe what I will do is next time, I will start with certain formalities. I will discuss them, and for instance, how this works. But today we don't need anything. We just need to remember some stuff. So enough injectives for sheaves of abelian groups can be done. And this is the path taken by Grothendieck. So he used these sheaves of abelian groups. He used this general machinery to do what? He used this general machinery to construct. So one gets cohomology for sheaves of abelian groups. And then if one wants to study cohomology of vector bundles or cohomology of quasi-coherent sheaves, then one just restricts the attention to these guys. All right. So this is already good. However, of course, it's almost impossible to compute such things. The most general thing, however, so from very basic, well, in quotes, basic arguments, you can get the following theorem by Grothendieck. That if X is an Noetherian topological space of dimension n, so I recall that Noetherian topological space means that all descending chains of closed subsets stabilize. And of dimension n, meaning that n is the largest chain of irreducible proper subsets, then for any sheaf of abelian groups, hi on x of E is equal to 0 if I is greater than the dimension. So this is a very, very interesting theorem, actually, and probably this is what we'll start with next time. But remark that it's incredibly, incredibly general. So it applies to arbitrary Noetherian topological spaces. So again, so we constructed quickly, and then we can't really compute anything. So let me give you another definition. So the second path is taken, well, by Serre, for instance, or other mathematicians. So another way to define the same things, another path, which is check cohomology. So let me define it for, so for now, I would define for nice schemes. So for instance, varieties. Actually, what I really need is I need, say, separated quasi-compact scheme. So pick this will be a very strange construction, but very efficient. Pick a covering X. It can be actually even infinite, U alpha, where U alpha is affine. This will depend on choices. The previous one depended on choices, but the choices were covered by the general machinery of cohomological algebra. Construct the following complex. Construct the following complex. This will be a complex, well, a complex of abelian groups, say, for simplicity, but let's say for quasi-coherent sheaves or vector bundles, what you wish. So the complex will be its nth term will be the product. So let's say this alpha, here alpha belongs to the indexing set S. Then its nth term will be the product of E of U alpha naught intersected with U alpha 1 intersected, etc., intersected with U alpha n, where we're running over all sequences alpha naught alpha n inside S. I will draw this complex in a second. So what is the beginning terms of this complex? First we have, I haven't defined the maps, by the way, but I will define the maps in a second. So first we take the product of E of U alpha naught over all alpha naught. It means that I pick a section over each open subset in my covering. Over each element of my covering, I pick a section. There's no compatibility condition between these sections. Then this should be mapped by the differential D to the product over all alpha naught alpha 1, E of alpha naught intersected with alpha 1. What will this differential do? Well, assume here I have a bunch of sections. Let me denote it S of alpha naught, this collection, belonging to E of U alpha naught. So this will map to the collection of S alpha naught alpha 1 belonging to E of U naught 1. Let me, for brevity, denote this guy by U alpha naught alpha n. So U alpha naught alpha 1, where S alpha naught alpha 1, well, how can we build it? Well, we can either simply drop alpha naught and take S of alpha 1, which is a section over U alpha 1. Here we have our first section, S1. Here we have a second section, S0, and we want to build something on the intersection. On the intersection, we take S alpha 1 restricted to U naught 1. Well, I keep writing this U naught 1. To the intersection, let me just write this. Minus, so I took S1, restricted it to the intersection, and then I subtract S0 restricted to the intersection. More generally, S for any sequence alpha naught, well, the differential of S of alpha naught alpha n will be the alternating sum -1 to the I S of alpha naught alpha I removed alpha n restricted to, well, the corresponding thing. Remark that this is a pretty big complex because I do not require, for instance, for an arbitrary set of elements, I can still take the intersection. And it can be very big. I can intersect alpha naught with itself enormously many times. But the important thing is that the cohomology of this complex, of this big complex, is the same thing as given by the previous construction. Exclamation mark. This is quite fascinating. Let's see even the first condition here. Well, it's very easy to see what is the first cohomology. The first, oh no, not this thing. The first cohomology of this complex is just the kernel of this map here, which I defined. But again, what is the kernel of this map? We pick a section over each open subset, and then we look at those sections that map to 0 under the differential. But what does it mean that it maps to 0? It means that for any pairwise intersections, if I take an element on the right, restrict, take an element on the left, restrict, and take the difference, then I get 0. But this is specifically a formal way of saying that I picked a collection of compatible sections. So what is really easy to see is to see that the kernel of this first map is always just the global sections. However, to see that the cohomology of the corresponding things give you genuine cohomology of sheaves, this becomes very non-trivial. And here, for instance, we started by picking a covering, requiring that each element is affine, which turns out to be very important, and then constructing a certain complex which depends very much on this covering, and moreover, it's very, very big. So this is some kind of magic that shows that this construction is actually does work. Well, one can make, turns out, one can restrict oneself to intersections of, well, smaller collections. As I said. And now a very easy thing, well, not a very easy thing, sorry. One thing that you can do is you can take X and cover it by U0 up to UN, UI affine. Say you have a finite covering. And then the complex that you build is first the product of UI. Then this maps to the product of E Uij over OI less than J. So you take intersections, you don't count them too many times. Then you have a map to E Uijk, where I is less than J less than K, etc. And this time this complex becomes finite. And let me just finish with a simple computation. So let's compute HI over our P1 of the line bundle of M. Well, as before, P1 is covered by U0 union U1. So there will be just two terms, and the first term will be the product. So if E is O of N, then E of U0 is K of T. I think it was K of T inverse. And then E of U1 is K of T, or maybe vice versa. And then if you put E of U naught 1 to be K of T inverse, then the complex that you get is the following one. K of T plus K of T inverse. And here, each element is a pair, a polynomial in T and a polynomial in Q inverse. And the map here, the differential, goes to K of T inverse. And the differential sends this pair to T the power minus N of P of T minus Q of T inverse. So this T to the power N minus 1 is specifically, we needed to identify the set of sections with the trivial module, and the restriction map is not trivial from the first component. It's restriction as the polynomial to a Laurent polynomial, but then multiplied by this T to the power minus N. All right, so by looking at this computation, this is the exercise. Compute H1 P1 of O of N and see that H1 of P1 of O of N isomorphic to 0 if N is greater or equal than N than minus 1. So there's no first cohomology. And then it's isomorphic, this is interesting, to S minus N minus 1 of V if N is strictly less than minus 2. So for instance, remember that we started by looking at this short exact sequence of minus 1 to the power 2, 0, 0. And we had this non-exact global sections functor, which took 0 global sections, 0. And here we have just the field K, well, C in our case. And now if you compute H1, then here, what you get is you get S0 of V. And V is a vector space, but the 0th symmetric power is just the field. So here you have K. And then our computation says that for minus 1 and 0, by looking again the computation here, the one that you should do, and the only thing that you should do is to compute the co-kernel of this map, which is this space. You need to quotient by the image of this map. So it turns out that here you have 0 and here you have 0. And this is precisely our connecting homomorphism, which gives you K. So as you can see, check cohomology, easy to compute, at least in some cases. Easy to compute. I mean, this can be done, this computation can be done by, I don't know, any first-year student who knows polynomials. However, to check the correctness and all the other things, it's very, very hard. So these are the foundations that I think everyone should know. And now we have 3 more classes. So here's our plan, big plan, kind of plan. Oh, plan. So lecture 2, we will discuss some technical details of cohomology. And we'll discuss application Well, at least two curves and surfaces. So, for instance, the Riemann-Roch theorem. Lecture 3, we will discuss higher push forwards and some advanced techniques. And as for lecture 4, I will try to explain how this all fits into a more general picture of derived categories and some applications. So, for instance, this will be, as for applications, I will explain how some vector bundles can be constructed using just the very structure of the derived category and how, for instance, it helps with, I don't know, something called twistor spaces. And these are exceptional collections. Well, I think I'm even a little bit over time. So if you have any questions, feel free.